Okay, good morning, everyone. I'm very happy to introduce Itzhak Tamo, Peter. He'll tell us about expander codes that are algebraic, very exciting new work.
Okay, thank you, Rick, for the invitation, and thank you for coming. So let me, first of all, feel free to ask questions. And so let me tell you about Algebraic Expander Codes. So this is a joint work with Swastika Cooperative from University of Toronto. And so before I tell you about Algebraic Expander Codes, let's do a quick recap what are expander codes. It will be on the same page. And so what are expander codes? So expander, also maybe sometimes my handwriting is not so clear. So let me know if something is not clear. So what are expander codes? So they were introduced in '96 by Sipser and Spielman. And they give us a way to construct a family of codes with very good parameters. And the way they do that is basically taking two kind of like independent ingredients. They take an expander graph and a local code of short length, and they kind of like glue them together. And then they generate the code. And these two ingredients, the expander graph and the code, don't have much in common except one parameter. So let me be precise. So if they take an expander graph, and where V are the vertices, V are the vertices. Let's say we have n of them, and let's say it is a D regular, and the E are the edges of the graph. And so this is one ingredient. The second ingredient is a local code, C0. And so what it is a code over some finite field F, some rate R, and length, the length of the code is D. So that D is the only parameter that connects the code with the expander graph. And so the length of this code is the regularity of, or the degree of the expander graph. And the way they glue them together or construct the code is the following. So the code is basically symbols on the edges. So you put symbols on the edges, symbols from the finite field F. And what you require is that if you stand on a vertex, you see D outgoing edges, you see D symbols. So you need to decide what is some type of ordering of the edges. So given that ordering, you see a vector of length D over F. And what you require that what you see is a code word of C0. And if this holds for any vertex, then you declare that this is a code word of your code. So that's the definition. Let's write it mathematically. So how do we define the code, the expanded code using G and C0? So what are the code words? Code words are functions on the edges of the graph. So all functions from the edges to your finite field, such that if I restrict F to a vertex, so what do I mean by restricting to a vertex? I stand on a vertex, I see D edges. So, and then I decide the ordering, and then I see a vector of length D over F. I want this to be in the code. And if this holds for any vertex, then this is a code word in my code. So that's the definition of an expander code. So now the two main parameters that you care about are the rate of the code and the minimum distance, relative minimum distance. So the minimum distance, or just in short, the distance of the code follows from the expansion of the graph. So if the local code is good minimum distance, and the graph is an expander graph, then this property propagates to the entire graph, and you have a linear distance. So the proof of the minimum distance follows from the expansion of the graph G plus local distance of the local code. Now, the second parameter that you care about is the rate of the code. So the argument about the rate is very simple. It's a simple counting argument. Why? Because in order for a function to be in the space, it needs to satisfy certain linear constraints. What are the linear constraints? The linear constraint imposed by each vertex. So if you count the number of variables, which is basically the length of the code, these are the number of variables that we have, and you subtract the total number of constraints, total number of constraints, if this is positive, then we know that there is a non-trivial solution to this set of linear equations.
So the constraints are independent, linearly independent.
I don't know. They could be, in fact, it would be very beneficial if they are dependent. But up here, we don't know whether they are linearly independent or dependent. But in the worst case scenario, they are linearly independent, and therefore, this will give us, if this is positive, it will give us something about the dimension. Then we can show that dimension is positive. So what I'm trying to say is that the dimension is that the dimension of the code is at least this. This is simple counting argument, number of variables minus number of constraints. So what is the number of variables? The number of edges in the graph. So you have n vertices and the degree is d. So this is the number of edges in the graph. And what is the number of constraints? We have n vertices. Each vertex imposes, it's a code of length d, and the rate is r. So the number of constraints is 1 minus r. Okay, so this is a lower bound on the dimension of the code. Now, if you normalize it by the length of the code to get the rate, so this tells you that the rate is at least, if you do the math, it is at least 2r minus 1. Now, if you want the rate to be the lower bound, this is the lower bound, you want this to be positive, then you solve it, you say that then you require that the local rate will be large, at least greater than 1/2. Now the question comes, what happens in the case where the local rate is less than 1/2? So in this case, we have more constraints than number of variables, and therefore if all the constraints are linearly dependent, then we are doomed and the dimension is 0. But if we still want to have expander codes with local rate less than 1/2, we need somehow that these many constraints should be linearly dependent, and therefore we can still have some positive rate or positive dimension.
Maybe add, why would we want the local rate to be less than 1/2? Maybe we want large local distance or other properties for the local code.
Yes, so there's a trade-off. Why would I want this? If I decrease R, then hopefully I can increase the local distance for some other properties. Okay, so let me tell you, so mathematically it's interesting, but then I tell you one more reason why might be interesting to consider codes with expander codes with local rate less than 1/2. So let me tell you about the Schur product of two vectors. So if you take two vectors v and w in Fn, their Schur product is, or it's also called coordinate-wise product or Hadamard product, is just the, as it sounds, coordinate-wise product. So you take vi times wi, and I goes from 1 to 2. So this vector. So you just multiply coordinate wise. And now you can define, if C is a code or any set, you can define the Schur product of the code with itself. It's just all possible Schur products. So C Schur product with W, where C and W are in your set C. And now we say that the code has the multiplication property if this set is contained in another code C prime that has some properties, interesting properties. Okay, so this multiplication property actually shows up in complexity and also in quantum fault tolerance. You sometimes need this property. So let me show you a code that satisfies this multiplication property. So if you take a Reed-Solomon code of dimension k, where k is less than n over 2. So what is the Reed-Solomon code? You just take a polynomial of degree less than k, and you oversample it at n distinct point. So if I take two such code words, and I take the coordinate-wise product of these two code words, I get basically an evaluation of a polynomial of degree less than n. Or so basically, this code word lies in a related code. What is the code? A Reed-Solomon code of dimension at most 2k, or at most 2k minus 1. Yes, because the degrees of the polynomials add up. And since the degrees, we start with k less than n over 2, the degree is strictly less than n, or even n minus 1, therefore it lies in a related code. So for this to hold, we know that the rate of this code, R, should be less than 1/2 to have the multiplication property. So now we have a problem. Let's say we want to construct an expander code with the multiplication property, and specifically where the local code is a Reed-Solomon code. So on one hand, we need that in order to satisfy the multiplication property, we need that the rate of the Reed-Solomon should be less than 1/2. On the other hand, if we want to have a non-trivial lower bound of dimension, we need that the local rate should be greater than 1/2. So it's kind of like contradicting. There's no such value of R that satisfies it. So now the question is, can you construct, very simple to state question, can you construct expander code where the local code is Reed-Solomon code, and you have you have positive rate for any rate, local rate R. So specifically for local rate R less than 1/2. That's the question. Question about the question? So what are we trying?
I have some different question, but I'm trying to understand how much this factor of 2 is related to like the choice, like the fact that we're working on an undirected graph.
Yeah, it's an undirected graph.
Like, I guess specifically, I don't know if it's easy to think about what this would do, but you could imagine like having two edges, two variables per edge, like one for each direction. Like, is this something sensible, or would it not solve the problem we're talking about?
What would, if let's say you multiply so each edge is both directions, yeah?
Yeah, so we have two variables.
What would it change?
No connection between the vertices.
If you only have one constraint that an edge touches, then you can, like, because these are linear equations, you can expect that like the distance won't be large, right? Because you can like.
No, you can't use.
You can just trade out one.
You don't use the graph at all.
I see. Okay.
Yeah.
No, what you do? Why don't you use the graph at all?
There's no this outgoing edge participates only in this.
Yeah. Okay.
Don't use stars.
Great.
So another question, if we already paused, is what the thing that's important in these codes is that after multiplication you have distance, or do you want like?
Yeah. You have some still value distance in the local code.
What I mean is.
So if once you have distance in the local code,
after multiplication, it also propagates to the entire.
Right, but this is the property that you're after. That
Yeah.
if you take two code words and you product them, you still have
Yeah.
you're still like
Have some sense, some distance.
Maybe I can also add that addition, codes give you addition for free because they're linear subspaces. If you also have multiplication, it's like allowing you to do computation underneath, like you're working on the level of encoding, but you're allowed to do addition and multiplication. So basically, you can do computation while remaining inside an encoding situation. So that's good for cryptography. Maybe it's good for other things. It's like a very useful.
but you can only do it once.
Right.
Okay, that's a different story, yeah. So now, if you want to do it multiple times, so maybe you take R to be much less than 1/2, maybe 1/3 or whatever. So you can-
I'm not sure you said before,
What?
you said before that you want this property. I don't see a property here. I just see a definition.
So I want, the property is that we say that this code has a multiplication property if the Schur product of the code with itself is contained in a related code with some good parameters. So code with good parameters, it's vague, but what does mean good parameters? The good dimension and distance, trailer.
Also, I'm just curious about what are the applications of such codes that are both multiplicative and expander code?
Yeah, so
in complexity.
what?
What are the applications of such codes, for example? in
So
complexity?
I think you're better to answer this question. So you want to repeat that?
I can just say that you can do like secret sharing and some kind of multi-party computation using these things.
Oh,
Or you can use them for PCPs. For PCPs, we use Reed-Muller codes, and we use the fact that we have multiplication because of this property of
I guess
polynomials.
I'm asking for multiplicative codes that are also expander codes.
Right, and so we already use this property in PCPs, but the rate of Reed-Muller code is not linear. So that means that our PCPs have like a polynomial blow-up. And like in a dream world, you can have a PCP with linear blow-up or a small blow-up using this kind of thing.
Oh, I see.
Okay, so let's continue with. Right, okay.
We have plenty of time.
Plenty of time, no rush. So keep asking questions. Okay. So I hope I convinced you that this is an interesting problem.
I can give you a hint that there's a big eraser and a small eraser depending on if you want to erase the board or just a little thing.
So you won't even have to erase for.
Oh yeah, this is you need over time. You need to you learn how to use these like huge boards and haven't figured it out. Yeah. So what is the right way to go up, down, or like this? Anyway, but pedagogically, what is the right way to do it? Anyway, let's continue. So, okay, so what is our construction? So in a high level, the original construction of Spielmann takes two kind of like completely independent objects. The only parameter that connects them is the t, the regularity, and combines them together. Our approach is maybe slightly different, is that we take one algebraic object. So it's the approach is completely algebraic. So in some sense, a lot of time you construct an expander graph using algebraic properties, algebraic objects, and then you forget that it came from some algebraic object, and you take another algebraic object, which is the code, and you combine them together. Here we're trying to do the same, everything at once. We have one object, so it's completely algebraic. So we have one object, and it's algebraic object, and the graph, the expander graph, basically emerges from this algebraic object. So the expander graph emerges from construction. Oh, expander graph. Okay, so what is the construction? I'll tell you what are the properties of the construction, and then I'll tell you maybe construction. So we fix some positive integer, at least 3, and some rate. This is the local rate. And you see it works for any rate, in particular r less than 1/2. N would be the length of the code and code length. So we give a code length. So we give an explicit construction of expander codes such that the local code, so maybe I write explicit construction, explicit construction of expander code with the following parameters. So the local code is the Reed-Solomon code, where the local length is order of n to the 1/8, order of, that's the local code. And the rate is more or less at most r. The local rate is at most r, more or less. And since it's a Reed-Solomon code, the distance is, the local distance is 1 minus r. Reed-Solomon code. These are the parameters of the local code. And the global code so the length is n, as I said, and the rate is some function, it's constant for fixed r and n. Not so important right now what it is. And the distance is more or less delta squared, the global distance. These are the parameters of the code. And now, so as you can see, we get the local codes are Reed-Solomon code, and it works for any r. So therefore, we can support the multiplication property. But the problem, there are two disadvantages of the construction. First of all, we see that the length of the local code, basically the sparsity of the graph, it is only polynomial in n. And we have to take m to be fixed. And the second thing is that the alphabet size is polynomial in the length. So in the original construction of expander codes, you don't, maybe if the expander graph is a constant degree, then you can also work over constant alphabet. So again, there are two caveats. The one is the locality or the degree of the graph, the degree of and the alphabet. So it is, for me, it's a very interesting question. Can you get codes with similar parameters? So Reed-Solomon code, expander codes, that the local codes are Reed-Solomon code, but the locality is subpolynomial. That would be a very interesting question to resolve. Okay. So what is the construction? So what is the construction? You take a Q to be a prime power, and M to be some positive integer, at least 2. And we define two groups. One group is the following a group of affine transformation. X is mapped to X plus G. Basically, it's a group of translation where G is in the field F Q to the M. Okay, and as a group, this group is isomorphic to the group F Q to the M with addition. So the group here, the group action is just a composition, function composition. And as a group, it's the same group. They're isomorphic.
Roger, what do you mean G is equal to X plus G? What is X?
X is the variable. It's a affine transformation.
This is an indeterminate?
Yeah. This is the polynomial X plus G. That's what I mean.
Okay, I see.
and then now I define another group, H, which is a group of scaling, so scaling transformation. So H times X, the polynomials H to X goes to H times X, where H is in FQ to the M plus 1 stuff. So I should say in the paper we define something more general and we give two instantiation of the construction. Here I give maybe the cleaner instantiation. Okay, so just all scaling by elements from the multiplicative group of this field. Okay, so now I look at the group generated by
Q to the M versus Q to the M plus 1, like what is that?
Y.
Yeah, what's going on?
Okay, I will get to it in a second. So, and now I look at the group A that is generated by G and H. So these are two groups, they are both affine transformations, a group of affine transformations. So I can look at the group generated by them.
In which ambient group?
I-
What is the big group that you?
So it's function composition. So it lies within some affine general linear group.
Sorry, but you're working over different fields, right?
Yeah, but so they all live under some huge field that contains both
So
of
you're
them.
taking like the smallest field that contains both of them, you're thinking about them.
Even the algebraic closure. I'm allowed to compose two functions here. And what I get is another linear function. They live in some huge field, both of them, over some huge field, whatever it is. Okay, so I look at the group generated by these two elements, and the group that is generated, I can actually write it explicitly. These are all affine transformation of this form, AX plus B, where A is in H, and B is in the field, in any element in the field, FQ to the M times M plus 1.
So that's the field that contains both.
Yes.
A in H means A is the multiplicative group of FQ to M plus 1. Is that right?
Again.
Yes.
A is in H means A is in that.
Yeah. A comes from this.
I see.
You could have called A little h.
Yeah, maybe it's better if they
That's
call it.
okay, but just wanted to.
Yeah. So A is in H. So yeah. Okay, maybe I should have said when I mean what I mean this. So I view H also. Oh yeah, I should have said it. Yeah. Okay. So this is a group of, I wasn't so clear. So this is a group of affine transformation, but as a group it is isomorphic to the following group. FQ to the M plus 1 star with multiplication. Right? And so I view this, so there are two representations of this group. So I can write it as this, and I write it as this. This is exactly the same thing. Any element here can be viewed as an element here, and vice versa. And when I write A is in H, I mean this. A is an element here. Okay? So maybe I should have. Okay. Okay, so this is the group, and I can actually calculate the size of this group, because for B, how many options do I have? I have Q to the M times M plus 1. And for A is an element in capital H, where basically it's an element here. It has Q to the M plus 1 minus 1. So now if I ignore the minus 1, this is basically Q to the M plus 1 squared.
M times M plus
Wait a
1.
minute.
Okay. No, I made a mistake.
M times M.
M cubed?
No, this is,
M plus 1 plus M plus 1 is M plus 1 times M plus 1. This
yeah. So someone in the audience agrees with me, so I'm good.
Okay, yeah.
As long as one person agrees, I think. Okay, so it's that if I ignore the minus 1, this is actually this.
okay, so going back to your question, so you see that these two groups don't talk the same language. One lives in FQ to the M and one lives with FQ to the M plus one. And what happens is that if I want to go to the smallest subfield that contains both of them, I need to go to a very large subfield. Basically, because M and M plus one are coprime. So this basically what gives us a graph, eventually a graph that it's not so, it's somewhat sparse. That's the whole idea. So using these two fields, because they come from coprime fields, so we get this sparsity of the graph. And the fact that one is translation, basically addition in the field, and the other one is multiplication, scaling. So these two proper operations don't work well with each other, and there's a lot of time they cause expansion. So this is what happens here too. So that's the idea of picking these two groups. So one is for a sparsity, and the other one, the sparsity comes from the fact that M and M plus one are coprime, and the expansion comes from the fact that this one is addition, one is the multiplication. Okay.
So like ideally, you'd like to replace these things with something that lives in something that's like even larger. The larger they generate,
Agree.
the more relative sparsity that you get.
Yeah, exactly. Okay, so we take this group, so that's the size of the group, and now so now we define the following field, FQ to the 2M, M plus 1. Okay, why this field? Because this field contains the field FQ to M, M plus 1, but it also contains any element from H. H is a FQ M plus 1. So basically what I can can view A as a subgroup of AGL, affine general linear group of F, or affine transformation on F.
Sorry, if you didn't have the two, what would go wrong?
Okay, so I would,
Later.
nothing would go wrong until something goes wrong.
Okay.
So for now, nothing goes wrong. Okay, but I can view A as a subgroup of AGLF for your question. What is the group? I can view it as two subgroups of this group. And now, so A acts on this field, very large field. So now what I take omega to be a subset of F, which is a regular orbit of A. So omega is a subset of F. Omega A acts on F, so it partitions F to orbits. So I take a regular orbit of A. What do I mean a regular orbit? Means that the only element in A that stabilizes an element here is the identity. All other elements move all the elements of omega. Okay? That's a regular orbit. And why do I need the extra factor 2? Then if the field is large enough, I can guarantee very easily that there is such a regular orbit. It's very simple counting argument, but you can actually found this explicitly. This
You just say that if you don't move, then you're like a root of some polynomial, and then you like say that there are...
Exactly. Each affine transformation stabilizes exactly 1 point. It's a linear polynomial. So it stabilizes exactly 1 point, and therefore the number of points stabilized by any non-trivial element here is just at most the size of the group A. But if the field is larger than the group A, then you can find one that is not stabilized. It's a very simple argument that guarantees that there exists such an orbit. So if omega is such an orbit, then we know that the size of omega is just the size of the group A, which we denote by n. That will be the length of the code. Okay, and the code will be an evaluation code. polynomials that evaluate on a set, which set? The set omega. So we will evaluate polynomials on the set omega.
Just to slow you down, so what's the best way to think about it? You now think only of the field F, and you have some collection, like a subgroup A of affine transformations, which are defined by looking at scalars from some smaller subfield, something like that. We kind of forget that, or
So A is just a subgroup. AGL acts on the field F, the large field. Okay, AGL is a group of affine transformation on the field F. I found, in a way, I defined a subgroup of this. The subgroup acts also on the field F, and then it partitions the field into orbits.
meaning if you start with some element in the field and you act by any element of A, you get an orbit.
Yeah, exactly.
It's not the entire field, it's
Yeah.
on the subsets of the field.
Exactly. And since it acts regularly, I know that it exists. There exists one that is a regular orbit. I know that the size of the orbit is actually equals the size of the set A, because no one here stabilizes an element because you moved all the time. So now we can forget about this field F. There is a group A generated by two groups, G and H, and they all act on a set omega that lives in some finite. Okay. Now, okay. Should go this way.
Maybe you could lower that middle board so we can see what's right then behind it. Thanks.
Okay, and what do we define next? So we define O. So A acts on the set omega, and therefore also the subgroups G and H act on the set omega. So each one of the subgroup G and H partition omega to orbits. So there are orbits that's coming from the action of G, and there are orbits that are coming from the action of H. So we put all these orbits in one collection, one set. Oh, these are orbits under G or H. So there are orbits, G partitioned omega to orbit, and H partitioned omega to orbit. So I put them all in one set. Now finally I can define the code. What is the code? C. The code will be functions from where to where, from omega to the field F. Wait. Functions, basically polynomials from omega to the field F, such that if I restrict omega to an orbit,
So it's orbits, it's.
wait. Maybe I want to write it differently. Okay, maybe I want to write it differently, like more explicitly. So these are polynomial evaluations. So I evaluate polynomial evaluations, such that the degree of F is small, less the degree of N is the size of omega. So the reason why I add this constraint, because I want the mapping from the space of polynomial that's to the code word will be injected. So I define this, and what I want is, if I look at I take a orbit, so now I look at my polynomial, I restrict my polynomial to the orbit. What I get is a polynomial whose degree is strictly less than the length of the orbit. Basically, I'm taking modulo the annihilator of the orbit. So what I want is So if I take f and I restrict it to an orbit, this is another polynomial. I want that the degree of this polynomial will be small. It is guaranteed that the degree of this polynomial is guaranteed to be strictly less than the size of the orbit. But I want it to be much smaller, so I want it to be less than r times the size of the orbit.
So this O is not the same as that O. That's the.
Wait, so this is little o.
This is little O and that's a big.
So I want this to hold true for all orbits.
Oh my God.
Is there a way to use a different letter than like little O and big O? And just
Big O, just do 2 circles or something like this. Make it bigger. You know what I mean?
Which letter do you prefer?
Uh,
2 seconds? Okay, maybe.
Yeah, בדיוק, ככה יופי. And also there. Okay. Thanks, okay,
thank you.
beautiful.
Now I said beautiful about my writing, the first one about beautiful. Okay, so we want that, so when we restrict a polynomial to a subset, so what we get is a polynomial of smaller degree. Smaller degree is strictly less than the size of the subset or the orbit. But here we want it to be much smaller. How much? R times the size of the set or the orbit. Okay, so this is the code. Now, what we need to do is to analyze the parameters of this.
So how much is the requirement that the degree is less than n actually necessary?
Because otherwise, you can, if you find a polynomial, you take a polynomial that satisfies this constraint, and you add to it some, basically the annihilator of the entire set, you get another polynomial that satisfies this.
Yeah.
And then if you include it in your message, the messages are polynomials. So the mapping will be the same mapping, so it won't be injective. So in this under code, it will be 0.
I see. Like as a space, it will be the same space even if you don't assume this, but you want to also like want to kind of think about the mapping here, so you're adding this condition. But like any
Because I want the code to have
right
sensible distance. Otherwise, the mapping in code is also an injective mapping.
sure.
No, but here, what your Tom is saying is that these, if you think of C as a collection of strings, then this is not important.
Yeah, I agree,
It's
I agree.
twice, doesn't matter.
I agree, yeah. At the set, it will give you these 2 different polynomials, give you the same chord width.
Can you explain again? I didn't understand this. I mean, I wasn't concentrating enough, but.
No, you're not the problem, I'm the problem, I didn't explain it.
Oh, we can argue about that. But, so F is a polynomial where? In
F is a polynomial, yeah, I agree, I'm a bit sloppy here. So F is a polynomial in the ring of polynomials. F. And F is defined.
Okay. And what is F? Restricted to O?
It's just, you just take, when I mean that is the smallest degree polynomial that explains F on this set. Or in other words, when I write F restricted to some set S, I mean F mod the annihilator of the set S. So annihilator of the set S is just what is H of S, is just the product of X minus little s, where little s is in capital S. So I divide and just take the divide by this annihilator polynomial, I take the remainder. So since I do that, I'm guaranteed that the restriction of F to S is a polynomial whose degree is strictly less than the size of S.
A polynomial that gives you as a function the same values on.
Yeah. So this 2 polynomial agree on the set S, on the value of the set S. But so here I know what is the degree of this polynomial. I know that the degree of this guy, so I know the degree of this guy, by definition, is strictly less than the size of the set. Because I'm F mod, a polynomial will give me the remainder will be, the degree of the polynomial will be strictly less than the degree of this polynomial. So I know that the degree of this guy is small, less than the size of S, but I want it to be much smaller than the size of S. Or in this case, O, I want that the degree will be much smaller than the size of the orbit, will be r times the size of the orbit.
Let me just add that it's not so unusual, like in Reed-Muller codes, when you restrict to a line,
You get,
you expect to get a degree that's much smaller than the length of the line.
good point, but I agree. Okay, so now we need to understand, so this is a very nice object, so why would it be a good code? So we need to argue about the rate or the minimum distance of the code. I mean, both. So maybe we say a few trivial observations on this code. So first of all, the length of the code is the size of omega. We just evaluate that, which is n. And the second thing is that since when I restrict myself to an orbit, I see a low degree polynomial, and I evaluate it at these points of O. So basically, when I restrict to an orbit, I see a code word of Reed-Solomon code, because I'm evaluating basically a low degree polynomial at many points. So I see a code word of Reed-Solomon. Now, each coordinate is parameterized by elements of omega. So each coordinate omega, little omega, is contained in two orbits. One that comes from the orbits under the action of H, and one is contained in an orbit under the action of G. So each coordinate participates in two local code words of Reed-Solomon. Agree? So this basically kind of like resembles what we see in the usual expander graph. In the usual expander graph, the coordinates are edges, and each edge participates in two local codes. One that corresponds to 1 to 2, the two vertices that the edge is connected to. So we can see exactly the same thing. Okay, so let's be more precise. What is I said that the graph is emerging from the construction. So what is the graph? So first of all, let's understand how orbits look like. So if I take an element in omega and an element in capital A, how an orbit looks like. An orbit of H looks like this. This is the right coset of H acting on omega. Yeah, so this is H times A. It's a set of affine transformation. It's a right coset of H acting on an element omega. So this is a subset of capital omega. And this is an H orbit. Because if you act from the left by an element in H, I get the same set. Yeah, this is it. And similarly, G times A omega is a G orbit. So this is how orbits look like, general orbits. Okay, so let's define what is the orbits graph. So the left vertices are the orbits, the H orbits. H acting on omega, H of A acting on omega, and so on. These are the left vertices. And the right vertices are the G orbits. So G acting on omega, G of A acting on omega, and so on. Now I connect, basically for each element in omega, I connect the two orbits that contain that element. So these two orbits contain the element omega, because they both have the identity element. G and H have the identity element. So they both contain the element 1 acting on the element omega. Now, also these two orbits contain the element A acting on omega.
What is A? Let's see what you have A in A, but then what are the others? What is the what is the role of this A? Yeah.
Yeah, it's a coset. It's the right cosets of A.
What are the other cosets? Powers of A, what?
No, I just, you pick a representative for the right cosets, and then I just write down all the cosets. This is a list of all right cosets of H.
Okay, but, and you assume that A, so A is not in H and not in G, so first.
Yeah. If this is distinct from this, then A is not in H.
So you just want one coset to be with the same representative, I mean.
I just write down all the right cosets of H.
Yeah, I'm just not sure what's the role of A.
A is just an A, in this case, since I wrote H, I'm trying to say that this is a different coset, so necessarily A is not in H.
Okay, just,
And not in G, otherwise it wouldn't appear.
No, it could be in G. Why?
Because of the right-hand side.
No, but this is a right coset of H.
but you also have a right coset of G with A. I mean, is A here in the second?
Look,
A is
H and
no
G,
element or any element?
H and G are subgroups of A.
Yeah.
So that I can all the time, for any element A in A, I can ask, this is well defined, and this is well defined. The right coset of H and right coset of
Yeah.
G.
If A was not in H but was in G, then the edge would have gone from HA to G. That way.
Yeah.
Yeah.
It's a graph.
You wrote in the top that you choose an element A, small a. So I'm not sure what.
Oh, and now, okay, I understand the confusion, because now the A I picked is not in H and also not in G. That's a problem, you're saying, yeah?
The problem is.
Yeah, but okay, so maybe I should have chosen a different representative, maybe B. But the point is that how do you construct a graph? The left vertices are the right cosets of H acting on omega. These are the orbits under omega, under H, and this is the orbit under the action of G. What?
Well, you shouldn't have changed it to B because you wanted to show intersection.
Yeah. But my point is, I want to, for any element in omega, so forget about the notation, right? What I have on the left side is a partition of omega to orbits. On the right side, I have a partition of omega to orbits. And each element of omega appears in one element in each partition. So I just connect these two vertices or these two elements in the partition that contain that element. And that edge as a label. What is the label? The element that is contained. That is the. Okay. So I can do this so what is the degree of this guy? So this guy is a set of size. What is the vertices? G of omega is an orbit of size G, capital G. So for each element, so it has this many elements. And for each element here, I draw an edge to the left-hand side. So the degree, the right degree, is basically the size of G. Agreed?
Wait, does omega, like little omega matter here?
No, it doesn't. It could be arbitrary.
I see, so you just fix an arbitrary omega
Yeah.
and here is the graph.
Yeah.
Okay.
But for any omega, you will give it the same graph.
Yeah.
So and the left side, so what I see here is again, the outgoing edges are labeled by elements from this orbit and so on. And the left-hand side is the size of H. So it's a biregular graph. And now, if you look for it, stare at it for a second, you say, basically, I don't need omega. So what I can define the coset graph. What is the coset graph? It's just the vertices are right cosets of H. And these are right cosets of H. These are the vertices. And on the right side, these are right cosets of G. These are the vertices. And what are the edges? The edges are for any A, E in A, little a in capital A, I define the edge HA with GA. Basically, I connect the right cosets of H that contain A with the right cosets of G that contain A. So this is the coset graph. This is called the coset graph. And this is, if you see it, it's exactly the same graph as here. What I'm trying to say is if you want to study the expansion of this graph, you might as well study the expansion of this graph because they are isomorphic. Now, what is the code? The code, as you can see, that in this graph, each edge is labeled by an element from omega. Yes? And now what is the code? We're evaluating the edges, the labels on the edges. And we know that the restriction to an orbit is a low degree polynomial. So what we see here on these edges is a chord word of Ritz-Holman code. So basically, this is the graph. It goes back to the expander code framework. We have a graph, and within each vertex, the local view is a chord word of Ritz-Holman code. That's the. So okay. So if you study, you show the expansion of this graph, and once you have the expansion and the local distance of the code, which is good because it's a Ritz-Holman code, it propagates the entire graph, and you get a linear distance.
So it's not a regular graph, right?
It's a biregular.
Yeah.
Yeah, it's biregular. So right degree is the size of J and left degree is the size of H. Okay. Questions? Okay. So I didn't say how you. So I just say prove the expansion. Once you have the expansion, and with the local distance, you get a linear distance, global distance. Now the second most important parameter is the rate. And now for the rate, you need a better grip. It's unclear a priori what is this? Well, what is the set of polynomials that satisfy this? You need to say something non-trivial about this set of polynomials. We know that, for example, constant polynomials are here. This is trivial, yes? But it doesn't give you much. We want to say something non-trivial. And
what you know is that polynomials of degree less than R times O for the smaller between H.
Yeah, I agree. You too. Yeah, I want to say that. I said, yeah, but I agree. Low degree polynomials of the form x to the I, where I is small enough, then they also live here. But I want something very, very large.
This won't get you constant.
They give you something of the order of the size of the orbit.
I think it doesn't depend on.
Which is very small.
Like
what?
Square root? What is it?
No, so it's a amplitude. Yeah.
So it doesn't depend on big omega, capital omega?
What is that? I say that it depends.
I mean, everything depends on your choice of the regular orbits.
So, my answer will be, in some sense weak. I can show a family of polynomials that satisfies this, which is independent of omega. Can you do something better with specific omega? Could be, I don't know. But I don't think it's a function of omega.
But I mean, ignoring this interpretation for a second, if you just look at your abstract graph, right? You have your local coefficients that are like, this is a coset graph. It's perfectly defined, even independent of like all this construction. It's just that. And now we look at the local constraints there. You have local constraints, and this is a perfectly good definition of the code, right?
Yeah, but if you can define an expander code on this graph,
right?
But it's the point is the mapping. So how you define the local code comes from the definition. In the original construction of Spielmann, this is not defined. You just say this is a Ritz-Holman code, but it's not well defined. You need ordering and the evaluation points. So already the ordering and the evaluation points comes from the definition.
Oh, I see. So you're saying.
So I'm saying I pick a very specific ordering and evaluation point. Basically, the evaluation point. This is what matters, and it comes from the construction. So so it falls under the framework of the original framework, but it's a very specific definition or instantiation.
Is the Sitzer Spielmann
It's hard to say. It's
Yeah.
super extreme, but it's like.
Is it,
That's
is it
double
fine if
S.
it's a bipartite graph?
What?
Is it fine if the graph is bipartite? Like it's
Yeah.
okay.
The definition was independent of
Well,
the
sorry,
structure of
I
the
mean,
graph.
it doesn't rule out the fact that it's an expander.
It's one-sided expander. That's what you want.
Okay.
Okay. Okay. So
Maybe I have one more thing, sorry.
yeah, go ahead.
In the beginning, Hanlin was asking you if the constraints are linearly independent.
Mhm.
And you said, well, if they're independent, then I need to do constraint counting and I get something. Basically, what you're doing is you're showing kind of a very special way to put the constraints on the graph so that hopefully they'll be much more dependent and
Yeah.
just counting will show.
Yeah, because specifically when R is less than 1/2, we know that you have more constraints than variables. So the simple counting argument tells us basically that the dimension is 0. Or not greater than not something negative, which is doesn't mean anything. Okay, so is it a good time to take a break?
Yeah, you're the boss.
Okay, so let's a quick recap where we ended. So basically what I'm trying to say, you can define, you have the coset graph where the left vertices are the right cosets of H, the right vertices are the right cosets of G, and you can impose constraints on each vertex to be a Ritz-Holman code word. This is exactly the same framework as Schipser and Spielmann. It's exactly the same here, but this is not well defined because once you want a Ritz-Holman code word, you need to say what are the evaluation points. And the evaluation point comes from our construction. It specifically tells you what are the evaluation points. And this in some sense, it's a natural, works more with the algebraic construction and this gives you a way to basically lower bound the dimension of the code in a non-trivial way. Okay, so now the question boils down once we argue that this is hand waved, say this is an expander graph, and then we argued about the minimum distance. The main obstacle is to lower bound the dimension of this object. That's the main obstacle. And for this, we want to give a new definition. As far as we know, maybe it was defined somewhere else. I couldn't find something similar. We want to define another definition of a degree of a polynomial. Okay. So if U is a polynomial of degree D, the degree of U is D, and D is positive. Okay. Now, if I look at the following polynomials, U to the I, X to the J, where I is non-negative and J is non-negative, but is less than D. Okay? I look at this set of polynomials. I claim that this set of polynomials forms the basis for this space of polynomials. Why? Because we have, for each degree, we have exactly one polynomial in that degree. Agree? Because J is strictly less than D. Okay? So this forms a basis for the space of polynomials, and therefore, if you give me a polynomial f, I can write it as follows. I can basically expand it in this basis. Or in other words, I can write it as summation of Cix U to the I, where the degree of each Ci is less than D. Agree? I can always write this for any polynomial. Now, so we define the U-based degree of f is once you write f in this expansion, the U-based degree of f is the maximum of the degrees of Ci. Oh, sorry. The degree of Ci maximum over I. Okay? Since the degree of each CI is less than D, this is well defined. Anyway, it's a finite set, whatever. It's still, we know that this is numerically less than D. Okay? So, it's sometimes a very natural definition, but I haven't seen it. I don't know if someone saw it, or you have to tell me if it's connected to something else. I don't know.
Because some power of u, then this degree will be 0.
Again.
Like if f is just u to the I, or u to the I plus u to the I plus 1 or something, then this will just be 0. Like
Yeah. So for example, yeah, if f is u plus u squared, for example, so then the degree u of f is just 0. Okay. So what do I want? This is the u-based degree of f, and now I want to define the following polynomial, g of x. G of x is the following polynomial, is the product of all affine transformation. G is a set of, it's a group of affine transformation. G of x, all the affine transformation in G, this is the product. Okay, so in fact, I can write it explicitly. I know what with this polynomial, this is the annihilator polynomial of the field of size q to the m. Okay, but more importantly is that G is acting on the field capital F. So but it also acts on the ring of polynomials over F. And what do I know about this polynomial? It is invariant under the action of G. So because it's multiplies all the elements of G, so it is invariant under the action of the element G.
Remind us, how does an element of G act on this polynomial?
It's just by
translation.
you act on the action is, so if I take an element G, maybe not G is not good, H in G, and F is a polynomial. So the action is, F. So it gives you another polynomial. Okay? But the point is, so if I plug in any element in here, I get the same. It's
So just to remember, G was the group of translations.
translations, yes.
So H inverse X is just X minus some.
Yeah, it's another translation.
Yeah.
It's another, but so it's another translation. So if
And you were claiming that.
that's a general definition of an action.
Now you were saying something about being the annihilator, and so what was the statement again?
So I'm just saying, G. Sorry. So this is the annihilator polynomial. So what I'm saying, Gx is G invariant. Yeah.
Meaning if you, instead of X, you plug in X plus some element in G,
Then you get the
you
same.
get the same thing.
Yeah, because we're running over all elements in capital. And G is a group. So we multiply. But the bottom line is if G is G invariant, little g is G invariant, it automatically tells us that G, little g, is constant on G orbits. It is constant on the orbits of G. So now I'm looking at the orbit of G acting, G is acting on the set capital omega. So G is a polynomial that is constant on the orbits. Okay, so why do I care about this polynomial? Okay, now that's the punchline, or maybe a little. So there's a small lemma that says the following. I'm after polynomials. I care about polynomials such that the restriction to the g orbits and the h orbits are small degree. So yes. So what the lemma says, so f is a polynomial of small degree, less than n. Let's say f is small degree polynomial. Then f, the degree. So if I look at the degree of f restricted to O is less than r times the size of the orbit, which equals r times the size of g, and for any g orbit, O, so I take a polynomial f that its restriction to any g orbit is small. This is exactly what I want. I want polynomials that the restriction to any g orbit is small. How small? R times the size of the orbit, which equals the size r times the size of g. Then this is equivalent. Okay, this is if and only if f satisfy this. If and only if the g-based degree of f is small. Now, so I'm looking at this. I want this type of polynomial, but it's equivalent to finding this. So this tells you why do I care about this g-based degree? Because it basically identifies exactly what I'm looking for. Okay, so now I can give an equivalent. So this is true also if I change g by h. So if I replace g by h, I get the same. So I can give an equivalent definition of the code. Maybe I write it here. What is the equivalent definition? What is the code? The code says all polynomial evaluations, exactly as before, and such that the degree is small, the degree of f is less than n. But now I replace these weird looking constraints by the g and h base degree. So I want that the g base degree of f should be small, and also the h base degree of f. Oh, I didn't define what is h. Okay, so h base degree of f will be small. Okay, and let me define what is h, the polynomial h. So I define the polynomial h here. So this is the definition of the polynomial g. The polynomial h is exactly the same. The product of all Affine transformation in H. And again, this is constant, this polynomial is constant on H orbits. Okay, so this is H, and we can actually write this H explicitly. It has a very nice structure. This is just the monomial x to the q times q to the m plus 1 minus 1. Great. Okay, so
Sorry,
what?
doesn't this just have a bunch of like? Isn't this just 0 q to the m plus 1 minus 1 times? Like, why is this? Why does this have any other 0? Like, is the minus 1 supposed to be outside of the?
The roots of this is just 0.
Right.
It's x to the something.
Right.
Okay, so I didn't understand the question.
So, all these little a sub x, these are all like a scalar times x.
Yes,
So of course it'll just keep giving you more powers of x.
you're answering him or answering
Yeah,
me?
I'm
Answering him.
That's right.
Yeah, you tell me.
H was just like a scalar multiplication.
That's correct.
Okay.
Why does this annihilate all the
It doesn't annihilate the entire field. It just annihilates. It has a zero with
it's not
high
necessarily
multiplicity.
an annihilator, it's
1, 0.
It's just supposed to have a polynomial that's constant on H orbits.
Yeah, but what I'm saying, this is what comes out. If you take all, you do this product, this is what you get. That's just a monomial.
Okay.
Okay, so the problem boils down to understanding these objects. All polynomials that are G and H base degree are small. And okay. And so now we can define this space of maybe before that. So let's try to understand this U-based degree, this new definition of a polynomial, of the degree of a polynomial. So let's try to understand if I look at U-based degree of summation of two polynomials. So f of g and in g are arbitrary polynomials. What can I say about these properties of U-based degree? So this is at most the maximum of the U-based degree of f and the U-based degree of g. U-based degree of g. So it acts similar as to a usual degree of summation of polynomial. It is most the maximum of the degrees, but this now you take the U degree, not the actual. Okay, so this is easy to prove. Another question: what happens with multiplication? So if I ask what is the U-based degree of the product of two polynomials? So this is at most the summation of the U-based degrees. So this is at most the U-based degree of f plus the U-based degree of g. So and as opposed to the usual degree where we have equality, here it is it's basically sub-additive. And so there are two remarks about this. So one remark is, if sometimes we have equality. Here, sometimes we have equality. So the first remark, if right hand side is less than the degree of u, then we get equality. So if this is strictly less than the degree of u, so in fact we have equality, and sometimes the bound is this upper bound is it doesn't tell you anything because we automatically know that this is at most less than the degree of u.
Can you kind of say a couple words on this, like to convince us that this is true?
Why this is true?
Yeah. Like maybe an example or just like.
Yeah. So let's start with the trivial case. If this is strictly less, this is at least d, then there's nothing to prove. D is the degree of u. If this is at least the degree of u, then there's nothing to prove because we know this is all the time less than d. Now we are not in this case, so the u-based degree of f and u-based degree of g, let's say, is strictly less than d. Okay, so let's write F as summation of Cix u to the I in this base expansion. And we know that the degree.
Don't mean to make you do all this complicated.
Yeah, so I am maybe, so the point is, so okay, maybe I write it and just say,
Because it's the basics, just if you multiply two expressions and if you multiply the two expressions and they're both of less degree less than d, you get some expression.
that it's already in base degree.
It's already
in the expansion that we want.
And if the polynomial, the CI, they're of degree less than d, then
Exactly. So basically, you get the convolution of the coefficients.
Every component has degree at most d and so.
Yeah, exactly. And
I mean, degree at most the sum of the degrees, and so.
yeah, but there's a point that they don't cancel out.
Right.
And so this is kind of like hand waving, but exactly what Doron said.
All right, thanks.
but this is if and only if, right? It's equality if and only.
I don't know. No.
I
Why?
have cancellation.
No, it can be.
But
If the
another
RHS is-
factor of you, like,
So what you're saying? What are you saying? You're saying that what?
If there's equality, then the RHS can be more than the degree because it can be.
If there is equality, then
The right hand side is mostly
that.
because it can be. I mean, this is trivial. This is more. It's easier. If you-
yeah. Wait. If there is equality, then the right hand side can. Yeah. This is true.
Yeah, that's what. That's
Yeah.
It's only.
Yeah. Agree. Okay, so let me show you where you don't have equality. So look at this polynomial. Let's say ux is just this polynomial, x to the d, and fx is just x, and gx is x to the d minus 1. So the product of f and g, this is equals to u. So therefore, the u base degree of f times g equals the u base degree of u, but this is already written in the expansion. So this is equals to 0. But this is less or equal than the u base degree of f. F is simply x. Since x is less than d, this is basically 1. And the u base degree of the other guy, since again the degree of this guy is strictly less than the degree of u, then the u base degree of g, so the u base degree of g is d minus 1. And this is, yeah, so, okay, so now after we have understood how this new definition of the u base degree behave, let's define the space of polynomial W. What is this W? These are all polynomials of degree less than n, such that both the g base degree of f and g and h are defined here. These two polynomials. The g base degree of f is small, and h base degree of f is also small. So this is a set. Why do I know that this is a subspace? Because if you add two polynomials, the u base degree is at most this, and therefore this tells you that you stay inside the set. So it's closed under addition and also under multiplication of the scalar. So basically it proves you that it's a subspace. Okay? And
You didn't need that because you also explained to us how to view it as an expander code, and we already know that that's a subspace,
yeah.
right?
Yeah. Yeah, because the mapping is linear, yeah, okay. Yeah, I agree. So it's another proof that it's indeed a subspace. Okay, so, and basically what we are evaluating, we're evaluating polynomial in this space. Yeah, so, and since the mapping is injective, we know that the degree of the code real after equals the degree of dimension of the code, dimension of this code that we're after equals the dimension of this subspace W. I'm trying to understand what is the dimension of this subspace. So, so that's the goal. And we're trying to make our life easier in order to analyze the dimension. So how I'm trying to prove something about the dimension, I will show you large set of polynomials that are linearly independent and they live in this subspace W. That's the goal. Yeah.
Like something very trivial is to count the dimension of things with like low G degree and things with low H degree, and kind of to just like count the intersection. Does this not work? Or
But how do they know? How do you know the intersection? That's the how many you want count?
I would just hope that oh, I see. Like it could be that the intersection a priori isn't like the count won't give you most polynomials. It will
Yeah,
give
how do yeah exactly? You want counting polynomials that satisfy only this is trivial. Only one of them. This is trivial.
Right.
Yeah. Okay. So that's the goal, to show you that there are many polynomials that are linearly independent and they are in the subspace W, and therefore it gives a low bound on the dimension of the code. So we try to make our life easier because maybe we're not smart enough. Then we say, okay, let's focus only on polynomials that looks like this. G to the I, X to the J. Okay? Okay, so if I want this polynomial to lie in the subspace W, it has to satisfy these three constraints. It has to satisfy this, this, and this. Okay, so let's write it down. So first thing is that we want that the degree of Gi X to the J will be small, but I can calculate it. What is the degree? This is I times the size of G plus J. And the size of G, I know it's X to the Q to the N, whatever it is. So we want this to be less than. Okay. The second constraint is that we want that the G base degree of G to the I X to the J to be small. But now I can use, before I require this, I can use the subadditivity of the G base degree. This is at most I times G base degree of G plus J times G base degree of X. This is by just subadditivity. Okay, what is the G base degree of G? 0. So this is 0. This is good. And what is the G base degree of X? 1. So this is equals to J. So we require that, so what we require that J is at most R times the size of G. So if I require that J satisfies this constraint, then of course, this is satisfied. Okay, so I'm relaxing a bit. So I'm just requiring that J satisfies this, and then automatically I get a bound there that my polynomial satisfies what I want. Now the last thing is the H base degree. of this polynomial. Which is, now it's unclear, how do you expand this? Now I need to expand this polynomial, which is in a different basis, and then to calculate the h base. So if I manage to find a polynomial of this form that satisfies, so what I want this, that h base degree will be small. How small? This one. So if I manage to find a polynomial of this form that satisfy that this polynomial of this form looks like it is defined by this pair I and j. So this I and j satisfies this linear constraint, satisfy this linear constraint, and somehow we manage to say something about I and j in this case, then we know that this polynomial lies in our subspace W. Okay, so if I take two distinct polynomials of this form that satisfy these three constraints, they have distinct degrees. Why? Because j is strictly less than r times the size of g, which equals r times degree of little g. So for any two I and j that satisfy these two pairs that satisfy this, we get two polynomials of distinct degrees. So therefore they are linearly dependent. So all in all, if I find a set, so everything boils down to, so count pairs I and j that satisfy constraints 1 up to 3. For any pair that satisfy constraint 1 up to 3, I know automatically that the corresponding polynomial lies in W, and they're all linearly dependent because they have distinct degrees. So now the problem is maybe somewhat easier. Okay, but the problem is, again, we need to say something about this. So now we need, up to now, we didn't actually use the structure of this polynomial, little h and little g. It was very abstract. Now somehow we need to get your hands dirty and say something about this, because otherwise it would be true for any h and g. Okay, so what is so we can say something, okay, maybe. So we define wk. What is wk? This is the h base degree of g to the q to the k. So we are acting a Frobenius automorphism on g. Okay? K times. So in this case, because Frobenius automorphisms are linear.
Sorry, G is our G.
G is written there.
H is also written there. Where is it? Yeah, it's just X to the Q.
Yeah, and G is written there.
And then what are you doing? You're
I'm raising it to the power of Q. Yeah.
Okay.
That's dimension of WP.
What?
That
No, this is maybe I should have, this is I use W because for weight, I call it weight. Maybe W is not good. TK. Let's call it TK. Okay? TK is just the h base degree of this polynomial. So in this case, we can say explicitly what are the h base degrees. If k divides m plus 1, this is q to the m. Okay? And else, this is q to the, k mod m plus 1. Okay, why? Because it's some calculation. Doesn't matter. Right, for now. But the important point is, so what do we conclude? Is that if there are two cases where the weight, this value, is equal to q to the n. where K divides M plus 1, or K mod M plus 1 is M. In other cases, the weight is Q to the at most M minus 1. So if K mod M plus 1 equals to 0 or M, then Tk equals to Q to the M. Else, Tk is at most Q to the M minus 1. Is small. Okay, why do I care about this? Because, right here. So now I want to understand the H-base degree of this guy. So I write I take I, the quadratic expansion of I write as follows: summation K, Ik, Q to the K, where Ik is, this is just the quadratic expansion of the integer I. Okay? Now I'm saying the following. What is the H-base degree of G to the I, X to the K, X to the J, sorry. I want to understand this. This is equal, instead of I write this. So this is H-base degree of what? Of the product over K of G to the Q to the K to the Ik. This is just G to the I. Times X to the J. Now I use subadditivity. So this is less or equal, this is by subadditivity, to the summation over K of Ik H-base degree of G to the Q to the K plus H-base degree J times H-base degree of K. This is by subadditivity. But now this is Tk. So, and this is 1. So basically what I get the summation over K, Ik, Tk plus J. So now if I require that this is small, if I require that this is small, then if I require that this is small, then this is small. Then satisfy this. Okay. Now, so this is basically the so I have 3 constraints. This constraint, so I'm going to ask, I'm trying to count the pairs Ij that satisfy this constraint, linear constraint, this linear constraint that J is less than this is easy, and this linear constraint. Okay? Now, how do I evaluate this? So basically, I claim that I can ignore this constraint. Why? Because what is my goal? My goal is to understand for each integer between 0 up to n minus 1, there exists exactly one pair ij such that the degree of this guy is actually equals to that integer. So among these pairs, I'm trying to understand what is the fraction of pairs that actually satisfy this and this. So this will give me the rate of the code. Yes? So I'm assuming that I'm only looking at pairs ij that satisfy this. I'm trying to understand the fraction of them that satisfy 2 and 3. And that will give me the rate of the code. So let me define an asymptotic version of these 2 constraints. So I'm looking at constraint number 2. So, okay, maybe I write it as follows. The degree of G is equals to R times Q to the M. So I define an asymptotic or normalized version of this inequality. I define J over Q to the M is positive and it should be at most R. So this is an element here. 0 over Q to the M, 1 over Q to the M. Yeah, this guy. Okay, and now this constraint. What is the right-hand side equals to R times Q to the M plus 1. And now I normalize everything by Q to the M plus 1.
So maybe is it intuitively correct? You have 2 constraints, 2 and 3. It can be very bad that they're kind of disjointed, nothing satisfies both of them. But if everything is kind of random and nice, then with probability R over Q, or probability R, you satisfy the first one. Maybe with probability R, you satisfy the second one. So you want to say with probability R squared, you satisfy. That would be like an ideal situation,
But the
right?
point is that they're a priori not independent.
They're not independent at all, but algebra is
But
sometimes.
no, but this will be nice because if you pick J, I mean you only need to pick J mod G and hope that it will be less than RG or normalize it this way.
J is always small. It's smaller than the size of capital J.
The point is that you can sort of pick I and J independently, right? Because J is like at most a degree of G, and I needs to be like 1 up to N over the size of G or something, right? So you kind of pick J independently, and you also have this like inequality that because J would be small, kind of you can basically ignore it and just hope that you pick I independently and it will work.
I totally agree. This is what happens actually. So I can maybe the correct version, but there's the same intuition. If you let Q tend to infinity, then the contribution of J does not. Okay, so maybe I do the analysis and then. Okay, so I just divide this inequality by Q to the M plus 1. So I get 3 prime. So what we get the summation over K and IK over Q times TK over Q to the M plus J over Q to the M plus 1 should be less than R. Agree? Now, let's define this object to be xk. So now, intuitively, what happens? TK, most of the time, it was written here. No, it was written somewhere.
Pull it down.
It was erased. So TK, most of the time, TK was most of the time at most Q to the M minus 1. Remember? And some 2 extreme cases, it was equal to Q to the M. So this term, most of the time, when Q tends to infinity, this goes to 0. When TK equals to Q to the M, does not vanish. Okay? So, and what happens to J? This is your intuition. J is very small. J over Q to the M is less than 1. Then if I divide it by Q to the M plus 1, when Q tends to infinity, this term vanishes. So it doesn't contribute anything. So it basically exactly your intuition. You can pick J independently of I, because they're coupled here, and this is equality, but as Q grows, it doesn't, the contribution is negligible, goes to zero. So my point is, when Tk is at most Q to the n minus 1 and Q is large, this tends to zero, so I can ignore it. And what I'm left with is the only case for which Tk is equals to Q to the n. So asymptotically, this is kind of like hand waving, but this is, you can make it more rigorous. You get the following inequality, and the asymptotic version. When Q tends to infinity, you get basically some summation over K, x to the K, xk, sorry, less than R. And what do you know about xk? Recall xk was ik over Q, so xk was in the set 0 over Q up to Q minus 1 over Q. Okay, and this is because I only considered, some summation over K where Tk equals Q to the n. Only in this case. And I know exactly when it happens, when basically this happens when K mod n plus 1 equals either 0 or n. Okay, and now the question is, what is the range of K? So I'm only considering I and J that give me something at most n, then you can give a K, it's not so important, but K goes from 0 up to m times n plus 1. Because I cannot be too large. So I know exactly, I can count exactly how many such K's satisfies this. So I know exactly. So most K's, or basically what it tells us, most IKs can be arbitrary because they do not appear in this summation. They disappear when K goes to infinity because this goes to 0. So the corresponding coefficient, the IK can be arbitrary. It doesn't contribute anything. So what now, once we take K, Q goes to infinity, we estimate it basically using Riemann sum, and we say this is basically, we have a polytope that is defined by this constraint, and K goes to 0 up to m times n plus 1, K mod m plus 1 equals 0, okay? And we have the other constraint, the asymptotic constraint is this. We call this Z. Z is, we have the other polytope is defined like this here. And also the xk are greater than 0. So basically we need to, this is a polytope defined by these variables, and we're basically trying to estimate the volume. So the volume basically gives you a count on an estimation of the number of pairs ij that satisfy. And then when you solve this is, you see that the volume actually equals omega of R. Okay, that's basically the proof. Maybe one last thing I would say, because I think it was a bit too much, that this is exactly what I told you in the office. So this approach, maybe I give a more summary of what we did, an abstract view of what we did here. And so what did we do here? If I give an abstract view of the construction, is the following. And I'm trying to say that this view of the construction has been actually very fruitful in other works. People also constructed other codes with locality, with interesting properties, and they use the same framework, but they didn't call it this way, but maybe it's a unifying way to view all this construction. So what is a construction? You have a group G that is generated by some set of subgroups, GT, and that acts regularly on some set X. Okay, so in the examples that we saw today, G was the group A that we call it, was generated by two groups. So T was 2. What?
We call it X omega.
Yeah, maybe I should have said shouldn't. Maybe I should use this. A and omega acts on the. So in our case, T was two groups, and acts regularly on the state omega. So X was some subset of some finite field. So in this example, or not X, omega, sorry. And in other instantiation of this framework, omega is the group itself. So the group acts on itself by multiplication. So I will tell you examples. And now, since the group, so now I replaced A. Hey, you should have said that this is A. This is not G. So they changed the notation for the group. So the group is A. So the group acts on itself. Okay, and now since A acts on omega, also each of the GIs acts on omega, and each one of them partitions omega to orbits. So let's define OI orbits under GI, orbits of omega under the action of GI. And now there's something slightly delicate. There is, maybe I just said without writing it, there is a natural parameterization of each. So now I look at all such orbits, union on. So I'm looking at all possible orbits under the action of GIs, each of the GIs. There are many orbits. So if I look at an orbit here, there is a natural parameterization of the orbit with elements in the field. It's kind of like hand waving, but this gives us the labeling or the way to evaluate our Ritz-Solomon coordinates. So there is a natural parameter. So if I take an orbit from this set, there is a natural parameterization of the element in the orbit by elements from the finite field.
Even in the small field, not this capital.
From some finite field.
From some finite.
Yeah.
This is what? This is a requirement you have from this.
It's from the examples that I'm going to state in a second, this is what happens.
Yeah.
So I won't write this, but this is basically what differentiates the construction from the original Shipster and Spielmann. Basically, it tells you how to evaluate, where to evaluate if you want Ritz-Solomon local codes. This natural parameterization that comes from the action itself, from the group action. And then what is the code? The code what is the code? All functions from the set omega to the field F, to some field F, such that, it's kind of like not precise what is the field F, such that the restriction of F to an orbit lies in a Ritz-Solomon code. It's a Ritz-Solomon code. It's a code word of a Ritz-Solomon code. Okay, so I'm not exactly precise, and we want it to be for all orbits in the set of orbits. So this is exactly what we basically saw in our example. Let me conclude that where this showed up. So when t equals to 1, maybe the simplest case, so there's a construction of optimal LRC, optimal LRC. LRC is locally recoverable codes. What they are, it's not so important. And this is by me and Bar. that basically gives a subcode of this thing, but it shows up, it gives the construction of optimal everything. And when t equals to 2, this is exactly what we saw today. When t equals to 3, oh, maybe. So there's example of I-dimensional expander code. This is by Irit, Yu, and Zhang. And in this case, the group is the special linear group. So all matrices of the determinant 1, and the group acts on itself. But the idea is the same idea. You get orbits, and then you restrict. You want that each orbit, your restriction to each orbit is the Reed-Solomon code word. And the last example is t equals to many. But this is many subgroups. So if I make it precise, anyway, the construction is called lifted Reed-Solomon code. This is an example of a locally correctable code, lifted Reed-Solomon code. This is by Guo, Party, and Madhusudan. And this is a construction of locally correctable code, and this also can be viewed under this framework. So, and the group here is basically the SQ to the N, just the alphabet space, and the subgroups are all one-dimensional subspaces. These are the GIs. So the GIs are one-dimensional subspaces. And the group acts on itself by translation. So this is anyway, so my point is that maybe this is a way to construct other codes with other groups or other actions to get better parameters. And let me conclude. There are many open questions, but I think the most interesting open questions is what I stated in the beginning, is to construct an expander code whose local codes are Reed-Solomon code, and for any local rate, specifically rate less than 1/2, where the locality or the degree is subpolynomial in the code length. That would be, I think, constant. You're very ambitious, optimistic. Yeah, or constant. So I think that would be exciting result. Yeah, let me conclude here.
Okay, thanks. Quick question before we go.
So have you tried?
No.
Okay. Have you tried looking at the other codes and trying to lower down the rate using this type of?
So these codes have. So already these codes have analysis of the rate. So you're saying, did we try to improve the rate of the low bound for these codes using this approach? Okay, so the point is you need to generalize what is the U-based degree of a polynomial for these are in this case these are multivariate polynomials. Okay, maybe I didn't say, but anyway. So these cases these are multivariate polynomials. So and then you need to generalize what it is. So I thought a little bit about this, and the answer is, I know the answer is, I don't know. I think you cannot improve it, I think. But I don't know how to improve it. Okay, so I think, but that's maybe the right way to put it. And also the same goes here. They did a very careful analysis, and the analysis is kind of like resembles what we did. And no, so the answer is no.
In fact, right. The lifted codes, that's where you see this expansion.
Yeah, exactly.
Degree, base Q and all this technology.
Exactly, it's very similar.
Yeah.
So, but again, the point is, what we showed, we only showed, we looked at polynomial of this form, g to the I, x to the j, that satisfy these three constraints. But it very much could happen that there are two polynomials of this form that do not satisfy this constraint, but some linear combination of them do satisfy it. Or another interesting question is, we know that this construction, when the local rate is greater than 1/2, is constant regardless what m is, just by the simple counting argument of the constraint. So for rate greater than 1/2, the rate is constant regardless what m is. It's independent of m. But once we go below 1/2, the only witness of the good dimension is this, is what I just showed you. But this set, what I showed you, is for rate less than 1/2, the rate is constant but for a fixed m. But when you let m grow, this goes to 0. This is in some sense bad witness. I said that doesn't give me much when m grows. So here in this case, when m grows, the rate stays constant. But in this regime, what I showed you, the rate goes to 0 when m grows, and it could be that it still stays constant for any m, even when m grows. So maybe there's a better witness. So let me just say, even for this case, well, for the I-rate regime, I don't have a good witness. Like I cannot show you large family of polynomials that are linearly independent and explain why we have constant rate independent of n. How do I know that the rate is constant? Just by the simple counting argument of the constraint. I don't have an explicit family that explains this for arbitrary n. The only family I have is this, but this one goes to 0 when m goes to 0. M goes to infinity. So I hope I was so I want a good witness, even for this simple case.
But the m shows up as a field size, is it?
Again?
M shows up as a field size, is it?
Yeah, m is just a parameter of the construction. You can tweak m to be as
It affects the alphabet of the code.
yeah.
That's a field size.
Yeah. It will affect the alphabet of code. But let's say you want very small. Yeah, I agree that alphabet grows polynomially with the length of the code. But let's say you want very large m, because large m gives you sparse graph. So I want very large m, or m goes to infinity. But if m goes to infinity, the rate goes to 0. But this in my witness, the family of polynomials that I showed you, that they are linearly independent. The rate goes to 0.
Okay.
I think I'm repeating myself, but anyway,
Questions?
Sorry, yeah, could you say anything about the analysis of the distance? Like, do you, or also of the...
where?
Oh, just for this, for thing you talked about today?
So I didn't say much.
Yeah.
I just said that the analysis is basically boils down to the traditional analysis. You show that the graph is an expander. So how do you show that the graph is an expander graph? You just do the traditional two-step walk on the graph, and you analyze the singular value or the eigenvalue of the corresponding adjacency matrix, and that's how it works. And it boils down to some Fourier analysis, but standard Fourier analysis. So you use characters.
Sure, the square is already like equal to the identity, and sorry, how fast does it mix like this?
So anyway, so we show that the single value is order of 1 over q. Okay, and then with the local distance, then we give something. And then what we take q to be large tends to infinity. So the second singular value, second largest, is small.
Your comment about the witness. So if G and H commute, then you get the complete bipartite graph.
Yeah, that's a bad expander because it's very
great,
dense.
There you have great witnesses that even beat this 2r minus 1 kind of bound.
Yeah, I agree.
Yeah, so maybe that would be one place to.
Yeah, okay.
The other question
Okay,
is.
so the point is, to loosen it, when G and H commute, there is no discontinuity with the witness. It's kind of smooth, no matter what R is.
Right.
The witness is kind of smooth, and it's actually also correct.
Right.
An upper bound on the rate of the code, and it matches, and everything's perfect.
This is the tensor code.
Yeah, it's just a tensor.
Yeah. So you want expander, and then you need to do something there.
Here I see, so the main intuition was that a lot of these IKs could be free.
Yeah.
And that comes from the behavior of TK, I think. So tracing back, I think is that the core property that you want from the groups G and H, that TK should have this behavior?
In fact, even if, let's say, all of the TKs were equals to Q to the L, let's say we're in the worst case. But what's good about it is that this would be, so basically the sum would be what? Over all possible Ks. Yeah? So where is it? Where's it's here. This is the asymptotic version.
Yeah.
So if let's say we're in all the TKs, let's say we're in the worst case that all the TKs equals Q to the M,
Right.
all of them, then the corresponding asymptotic version would be summation over all Ks without this constraint.
Yes.
This still gives you a low bound because if the volume of this, because this is you have a finite number of variables, the volume of this still positive.
For a constant M.
Yeah, exactly. So it just gives you a not so like a worse estimate.
Sure. Okay.
Okay, maybe let's take all other questions
Okay.
offline. Thank you so much.